Hi everyone, I'm Alexander Winkler and I'm going to present some work that we've done together with my colleagues Jungdam 1 and Yuting. So we're at Meta Reality Labs and Meta AI Research, and we're going to talk a little bit about our paper Human Motion Tracking from Sparse Sensors with Simulated Avatars. So the first question is, why are we even talking about sparse sensors? What's the motivation for that? And one motivation is that sparse sensors are becoming more and more popular in consumer products. So a lot of the virtual reality devices, such as the Quest headset, have very limited sensor information to observe the human body because they are worn on the human body. So they have sensors that look outside to do some SLAM. They have some controllers, some IMU sensors in the controllers, and also some state estimation in the headset. But they don't have a lot of information, for instance, about the legs. So there's no external cameras that are watching the legs, so it becomes very difficult to reconstruct such poses like that. So that's one motivation for this research area, trying to reconstruct some poses from this very sparse sensor information and construct full body human poses. So the existing approaches in this area of reconstructing a full body pose from sparse sensor information could be clustered into two categories. The first could be kinematic approaches and the other could be simulated approaches. And here you can see three recent kinematic approaches, and the commonality is that they all train on a large motion capture data set and poses, and then doing inference they learn to fill in the missing information of, for instance, the lower body with a pose that's most likely that they've seen during training in the data set. Now, this type of filling in, or you can almost say interpolation, can cause some issues that the filled-in poses might not be physically correct. You can see that, and it might introduce artifacts like foot sliding or foot jittering. So for that reason, another direction that's explored and that I mentioned is simulated approaches. So in simulated approaches, the character is simulated in a physics environment, and the input to this physics environment are actual torques that drive this character. And this has the advantage that all the poses, are physically correct, and you can remove some of the artifacts that you might see in kinematic approaches, such as foot hovering or jittering. So this is also the type of approach that we've taken in this work. So our contributions are that we take in the sparse sensor input, so we don't work with images as in some of the previous work, but we directly work with the position, or we only work with the position and orientation of the headset and the controllers. And output is a fully simulated character. And specifically, we really emphasize we're able to produce good quality motions, so physically simulated. We don't use any root forces to drive the character. So all the entire motion comes from torques applied to the joints. We show that we can track dynamic motion, so quick directional, some jogging with some quick directional turns, as you can see here. We also show that we can track users of different sizes with the same train policy, and we achieve this with a simple RL architecture that's trained end to end. So here you can see an overview of the reinforcement learning architecture, specifically the inference. So on the left-hand side, you can see the input, the Quest position and orientation goes into the policy and is combined with the state of the simulated character. And these observations are passed to the policy as input, which is the neural network that we actually train. And the output are, in our case, torques that are applied to the physics simulator, which then does the forward integration and produces the state of the simulated character. And that's the character that we actually visualize with a mesh then afterwards. And so the main thing that we have to train in this setup is the policy, the neural network. So how do we actually get the policy to produce torques that somehow make the simulated character follow the user that's wearing the Quest headset? And we use a standard imitation learning reward for this. So we have a motion capture database of about 8 hours of motion capture data. And from this data, from these skeletal poses in this motion capture database, we can synthetically generate the poses of the Quest controller and the Quest headset. So we know, for instance, in this motion database where the wrist is, so we can offset the wrist by a specific amount and assume that there's a controller there. And the same, we can place a frame between the eyes, which would resemble the Quest headset. So we can generate this pose synthetically, feed it into the policy, and the policy then produces a torque that creates a simulated character state. And if we have that simulated character state, the objective is that the simulated character has the same pose as the ground truth motion capture data that we used to synthetically generate the Quest positions. Because we know that that would be the pose that the user's standing in if this were the sensor information of the Quest headset. So we have the full ground truth mocap pose of the character. We compare it to the simulated character in with standard rewards such as in Deep Mimic, and we use that signal to update the policy. So that's the high level overview. And one reason why we hypothesize that this works so well, because the information of the Quest input is very sparse. It's just a few numbers of position and orientation, whereas the tracking works fairly well. And one reason that we think this works well is that we have this very dense supervision during training. We know exactly what the pose of the user is supposed to be, so we have some very strong signal during training to move the legs at exactly that position, even if that position is not actually passed as observations to the policy, but just provided as ground truth motion capture data. And another reason why we think that this works well is because of this feedback loop from the simulated character back into the policy. So the actual observations of the Quest headset, of the sensor, only make up about 30% or 20% of the total observations that are fed into the policy. The other 70% come as a feedback from the current state. And this is a very strong prior for the policy to disambiguate what type of action to produce now. So even if the sensor information is fairly similar, it still can rely very strongly on the current simulated character state to produce the correct torques. So this could be sort of imagined in a more supervised learning way as like a recurrent neural network. And this is a very strong prior that helps make sense out of this very sparse Quest sensor information. So our motion capture dataset that we use for training consists of motions that are typical motions that a user might do in VR. So it includes like walking motions, jogging motions, some standing motions, and some gesturing motions. And with that, we use a GPU accelerated physics simulator, Isaac Gym, to imitate these motions, 4,000 characters in parallel. And each of these characters returns back a tuple of observations, actions, and rewards. And then we use those to estimate the policy gradient and update the policy weights, so according to proximal policy optimization. And the advantage is that this type of GPU acceleration helps us to train our policy in about a day. We already have a fairly good policy that's able to imitate a large amount of motion capture data. So once we have this policy trained, here you can see some motions on real sensor data. As you can see, the character is able to track the motions fairly accurately, even though there's some quick directional turns that the user is doing. So it's able to predict the correct torques that have to be applied to the joints in order to, as close as possible, get these match the headset position and the hand's position. And we show that the same policy can work on different types of users. So the user before was about 1.65 meters, and this is me at about 1.80 meters, and it's the same policy that's able to track these different types of users because the scale of the character is part of the policy input. And if I pause this at specific times and we observe the state of the character, we can see that the foot positions are very closely aligned and it's able to, from these poses, quite easily distinguish what the lower body pose is. So the question is how is it able to do that? And here's just a possible explanation of how much information is actually in that sparse sensor data. So if we look at these dark lines which come from the headset, XYZ, and we look at, for instance, the walking section here, we can see that there's a nice pattern here between the controllers oscillating forward and backwards across the headset position, basically, which is seems like a very distinct pattern for a walking motion. And then once it goes to a jogging motion, you can see that this oscillation between the controllers and the headset stops. They're basically aligned. But for that, we actually have a very distinct oscillation up and down of the head, and the controllers oscillating at a very high frequency. So there is some patterns that probably help the policy to determine the correct gait and apply the correct torques. But it's not as this is just a guess at what the policy might be anchoring to. Now, if we have even sparser sensor information, such as these motions here, where the only input is just the headset without the controllers, and you can see that the torques produced for this character are still driving the character to very similar poses as me wearing the Quest headset. And if I pause it at specific times, you can really see that even the foot lift and the foot plant are very similar to the actual ground truth in this case. So I'm just pausing it here, and you can see that the toe touching and the foot touching, they align very well. So that was surprising. Now, what's definitely more difficult to imitate are non-cyclic movements. So if there's not a strong correlation between the upper and lower body, for instance, with walking, the arm swing often corresponds inversely to the leg motion. It's more difficult for the controller for the policy to track the motion. I think that's related to the fact that there's probably not as much sort of uncorrelated training data in the training data set, but also just in general for the policy to figure out a pattern to correctly synthesize this very ambiguous sort of lower body pose when there's multiple poses that might correspond to such a non-cyclic upper body movement. So here you can see some of those examples. Now, one thing that we can do, since we are fully simulating the character, is that we can add other simulated objects into the scene. So in this bottom example, we added a simulated ball and a simulated box to the scene, and you can see that there's a two-way interaction. On the one hand, the simulated character actually moves the simulated object, the ball, and it bounces around because the simulated character has collision geometry and accelerations. And on the other hand, also the environment can affect the simulated character. So the environment causes the simulated character to fall, because it is not just driven by the user, but it's actually also fully in this physics simulated environment. So this sort of poses some questions on when should we actually follow the user and maybe override the physics, or when should we follow the physics and ignore the user input. And here's another example that shows how the simulated character is able to adapt to different types of environment and is actually influenced by the environment. So in case if we place rough ground into the simulated world, the avatar will have a different gait, so it'll be following the user, but also adapting to this type of style to make it believable that the avatar is actually moving inside this world. And since we trained the policy on a variety of different users, so we had about 172 different users in our database, we can actually initiate different sized simulated characters to track the same user. So here you can see a simulated character of the same size of the user, about 167 centimeters, and then a much taller, 25 centimeter taller character. And you can see that both of these simulated characters are still able to track the user, but they have very different poses. As you can see that this character is actually crouching but nonetheless there's no floor penetration or any other artifacts that you might expect when you would do a simple kinematic retargeting, because it still has to obey to the laws of physics. So this can be seen as a very simple maybe retargeting problem. In the future we want to be able to use simulated characters that are even much more different than a user. So some limitations in future work that we're looking into right now. So one of the things is the animation quality. There's still the animation, even though it obeys physics, the animation itself doesn't quite look natural. It looks a little bit wobbly at times. So we want to work on this type of animation quality. The other one is the skill set. So I think this is where this distinction between kinematic and simulated approaches is also relevant, that kinematic approaches, they're able to track a wide range of motions, and even if they can't exactly track a motion, they'll still find some reasonable estimate of that pose that might have some artifacts but still roughly follows. On the other hand, in simulated approaches, it's different in the sense that it can track the motions that it can track. It might track very well with little artifacts, but for motions that the character cannot track, it might fail completely, and the character will just fall if it hasn't learned that skill set. So it's a little bit more of a risky approach that has stronger oscillations in both directions, I would say, and we want to work on increasing the skill set of these dynamic approaches and of these of the policies. Another aspect that that we want to work on is the delay. So in the videos that I showed, we actually shifted the input by 150 milliseconds in the videos to show what was the objective of the policy, but in reality we allow the policy to look 150 milliseconds into the future in order to best anticipate what the user is actually going to do and already adjust for the inertia and the movement to best track the user. And that of course causes a delay in real-time tracking and will be uncomfortable if a user is actually looking at their own body, for instance. So this is a direction that we want to look into and try to reduce that delay. And finally, the environment interaction. I think physics is very well suited for interacting with the environment. We get contact forces and collisions for free, and I think it would be great to use some of that information to track motions or produce motions that have more interaction with the environment than just the flat floor. Yeah, so those are the most direct paths that we want to pursue in the future to improve on this work. And yeah, thank you very much for listening.